All right, let's talk about a piece of technology that completely changed the game for anyone who builds software: Docker. We're going to break down how it takes an application from a single laptop and makes it run reliably absolutely anywhere, from a test server down the hall to the massive world of the cloud.
You know, it all starts with this one dreaded phrase. I'm sure you've heard it, you've probably even said it. It's that classic, super frustrating moment when your code runs perfectly for you, but the second someone else tries to run it, everything just breaks. All because of tiny, invisible differences in computer setups. This was a massive headache for the entire industry.
And this is where Docker just swoops in to save the day. It tackles that my machine problem head on by packaging up an application with literally everything it needs to run: all the code, all the libraries, all the little dependencies into one standardized unit. We call it a container. You can think of it like a perfectly sealed box that ensures your app runs the exact same way every single time, no matter where you put it. Okay, to really wrap your head around Docker, there are two words you absolutely have to know: images and containers. And the best way to think about them is with a really simple analogy: the difference between a blueprint and an actual building. So first up, the Docker image. This is your blueprint. Simple as that. It's a static, read-only, totally unchangeable template. It has all the instructions and materials needed to run your app: the code, the tools, everything. You create this blueprint by writing down a list of instructions in a special file called a Dockerfile. So if the image is the blueprint, what's the container? Well, it's the actual building. It's the live running version of that image. It takes all those read-only layers from the blueprint, and then, and this is the most important part, it adds a brand new writable layer right on top. This is the magic ingredient that lets your running application actually do things, like create files or write to a log. All right, let's just put it all together side by side so it really sticks. An image? That's your unchangeable template, made from a Docker file. A container? That's a running instance of your image, and it's changeable thanks to that special writable layer. The key takeaway is simple. You build an image once, and from that single blueprint, you can spin up hundreds, even thousands of identical working buildings.
So you might be wondering, how does this actually work? How does Docker create these little isolated worlds for our ops to live in? Well, it's not exactly magic, but it is a pretty darn clever use of some powerful features that are already built into the Linux operating system. So let's pop the hood and take a look. It all comes down to three main pillars, the secret ingredients, if you will. First, you have namespaces for isolation. Then you have control groups, or C groups, for managing resources. And finally, union file systems, which give us incredible efficiency. Let's dig into each one real quick. First up, namespaces. This is all about what a process is allowed to see. It's the heart and soul of isolation. Basically, each container gets its own little bubble, its own private view of the system. It has its own process IDs, its own network, its own file system. It's literally like putting blinders on the application so it thinks it has the entire computer all to itself. Okay, so if namespaces handle what a container sees, our next pillar, C groups, handles what it gets to use. This is all about managing resources. C groups let you say, hey, this container can only use this much CPU and this much memory. And that's so important, right? It keeps one greedy container from chewing up all the resources and crashing everything else on the system. And our third pillar is union file systems. Now this is where we get that awesome layer cake we were talking about. It's what makes Docker so lightweight and fast. By stacking all these read-only layers from an image, it allows different containers to share the common parts. Think about it. If you have 10 containers that all need Ubuntu, you're not storing 10 full copies of Ubuntu. No way. You store it just once, and they all share that base layer. It's a huge space saver. So this whole layer cake thing, it's not just a cool party trick for saving disk space. It's actually the key to making Docker an absolute powerhouse in modern software development pipelines, a process we call CI/CD. That stands for continuous integration and continuous delivery, and it's all about moving fast without breaking things. Picture this typical workflow. A developer pushes some new code. Instantly, an automated server grabs it and builds a brand new Docker image. Then, that fresh image is spun up as a container to run all the automated tests in a perfectly clean, predictable environment. If everything passes, that exact image gets pushed to a central storage place called a registry. From there, it can be deployed into production. The beauty here is that the exact same thing that passed all the tests is what goes live. No more surprises. So, running one or two containers is pretty straightforward. But what happens when you're running a massive application? I mean, we're talking hundreds, maybe thousands of containers all working together across a whole bunch of different machines. How on earth do you manage all that? Well, that's where orchestration enters the picture.
Yeah, at that kind of scale, you need a boss. You need a conductor for your container orchestra, something to manage the deployment, the networking, the scaling, all of it. And for pretty much everyone in the industry, that conductor is a tool called Kubernetes. Now, how does Kubernetes, the big boss, talk to the little worker bees that are actually running the containers? It needs a common language, a standard protocol. That standard is called the Container Runtime Interface, or CRI. The best way to think of it is as a universal plug. As long as a container runtime has the right socket, Kubernetes can plug right in and start managing it.
And this is super interesting because it led to a really big shift in how things work. The old way was kind of clunky. Kubernetes had this built-in translator called Dockershem to talk to the full Docker engine. But translators, they add overhead and can slow things down. So the new way is much smarter. Kubernetes uses that CRI standard to talk directly to a lean, mean, purpose-built runtime like Containerd. By cutting out the middleman, the whole system got more efficient, more secure, and just plain better at running containers at a massive scale.
So let's zoom out for a second. Docker and this whole container ecosystem solved that huge, nagging problem of it works on my machine. They gave us true portability and standardized how we run software. And that's really how technology always moves forward, right? We solve one massive problem, which creates a new stable foundation, and that new foundation inevitably lets us see the next big challenge on the horizon. So I'll leave you with this. What do you think that next great problem will be?